Hi, my name is Gleiben. I'm doing Raspberry Pi Lab 4. First I'm going to go over the gpio.s, main.s, and timer.s files and what it uses for the code of this project. Okay, so we go over the global GPIO address. It takes the GPIO address, requests register 0, then it loads the GPIO address, which is 020000. It moves into return address and does the program counter, and then the GPIO address sets the GPIO address registers the address by register 0 to low 3 bits of R1, register 1. So we have a pin number request, which is register 0, and pin function is register 1. Then it compares the pin number with 53, which is from 0 to 54, I believe from 0 to 54 pins, 0 to 53 pins, and then it takes the pin function, which is 7, which takes from 0 to 7 for each pin and out of 53, and then it does move high PC, move high, and then returns the address to the program counter, and then it pushes the return address, moves the register to pin number, and then the GPIO address request is it takes register 0, and then it compares to the pin number 9, and then top high pin number 10, and then add high GPIO address 4, and then it loops the function again. Then we add the pin number, left shift number 1, so it masks the register 3. Then we move the mask number 7, which is R3 equals this binary number. Then the R3 equals the binary number where the 111 is the same position as the function in R1, and basically the same information here, which it does to R1 using different binary number for the same thing. Then we load the old function from the GPIO address into register 2, which is existing code. Then we load the R2 existing code with bits, and for this pin all 0, and then we pin the function with old function, request existing code with correct bit set. So the pin function and the GPIO address is set already, and then it on rec at rec, which does pop for the program counter. So if the GPIO sets register 0 if R1 is not or equal to 0 and low otherwise, then because it uses 32 GPIO registers and 32 values, so basically we have a pin numbers register 0 and pin value register 1. So it compares the same thing, basically does the same thing over again, and then it does the pin number 31 is set bit with register 0, register 3 I mean, and then it moves the set bit with number 1, shift left, set bit with pin number, and then pin number becomes unrec, which is deleted, I think, deleted alias. So do deleted alias again, pin value, and it does the GPIO 40 and 28, probably to turn on and off the LED. That code does turn on and off LED using this address, and that's it. So I'm gonna go to main.s file. For the main.s file, using still Alex's Chadwick's code, and it's going to be using system directives, which is section.unit and global.start colon. So in this one, we're using a stack pointer at this bit or address. I think it's bit, yeah. And basically, we move registry 0. This is what the function is of the GPIO port 16 for the OK LED to be 001 binary. So you're going to use 0 registry 0 GPIO pin 16 and move registry 1 to pin 1. So our registry 0 is 16 and registry 1 is 0. So we set the GPIO. Now we add the new function here, which is going to be using a value of 100,000 microseconds for the delay causing the LED to flash 5 times per second, which is the LED 0. Loader, it's going to be loader registry 0, which equals 100,000 microseconds, and then wait, and then we use the new GPIO value again for another 100,000 microseconds for for the delay causing the light to flash 5 times per second again, using move with GPIO 16 pin, and then move register 0 with GPIO 16, and then move registry 1 with pin 1 for the GPIO for both of these values. And then we're gonna use our new method, use the value of 100,000 microseconds for the delay causing the light to flash 5 times per second, and then loop this process forever more, repeating itself. So now I'm going to explain systemTimer.s. This is a timer, and it uses the system timer base, global get system timer base, and it's going to load the address 020003,000. Move the return address to program counter, and basically it's gonna get the timestamp, which is gonna create the return address in registers 0 and register 1, with register 1 being most significant 32 bits. So basically this is what it does to the code. We get the timer stamp, we push the return address, get the timer base, and then we do loader for register 0 and register 1. Register 0 is pin number 4 out of from 0 to 8, from 0 to 7 I mean, and then we pop the program counter again. So now it waits at least the specified number of microseconds before returning duration in registry 0, and now we're gonna delay registry 2 and then move delay to registry 0, and then do the same thing, which is gonna push the return address again, get the timestamp start, and then it moves to start to 0, registry 0, and then it's gonna loop, apply the loop again using the similar code, which is get timestamp, and then the sub is elapsed with registry 0 to start, and then compare the elapsed delay with the loop, and then it will delay to start with a pop program counter again. So I'm gonna show you the CMD, how to generate this the kernel image using lab4 Raspberry Pi. So I'm going to my bin file, make sure there's no extra files there. Okay, now I'm gonna go into my source file, make sure this is the 4th lab. Okay, copy this thing and then paste it here. Yes to all. Now I'm gonna do pymake. We get this like a small thing that we have to do, extra step before we get the final image, and then paste it here. Now I'm gonna do pymake again. We get this error, the build error. So to fix this error, I use my make file. Copy this make file, put it into the bin, and now I'm gonna do pymake again, and it generated the image successfully. Thank you for watching. Bye. And don't forget to watch my demo video, be separate from this, because I'm recording through Cam Studio and I don't have a webcam on my computer, so I have to use my iPhone to record the demo.